to, I usually like, sorry.
Yeah, you can go on. I just hit record. Yeah.
So I usually like my talks or lessons to be very interactive. So Khadija, I heard you say we should wait till the end with questions, but we can also engage me as we go along. So I prepared a Mentimeter to get us started on an interactive note. So I'm going to share the link, the chat box. Just 3 questions. 3 questions. I would like to find out where you are joining us from, and also a bit about the background, a bit about your background. So I'm going to share my screen now and also put the link in the chat box. So if you can go to menti.com, I'm going to put the link quickly in the chat box. If you can go to menti.com and use the code. So let me share my screen so you can see. Okay, great. Yes. So if you can go to menti.com, I've also put the link in the chat box. If you go to menti.com and use the code 87532949, I would like to hear from you. Firstly, what is the name of the city or the town you are joining us from? What is the name of the city or town you are joining us from? So I'll wait for, okay, we have already, oh, Accra, great, because it's the Accra chapter, right? Definitely Accra will represent Port Harcourt. So great, from Nigeria. Kigali, okay, Rwanda, okay, Saarbrücken, I'm sure it's Deborah from Germany. I might be wrong though, correct me if I'm wrong. So I think Nairobi. So we have West, East, Dublin, yes. Yeah, Khadija, I guess you joining us from Dublin. Okay, Addis Ababa, brilliant. And Meba, okay, that my geography is not so great. I don't know where that city is. I'm sure I'll check it out after this. Okay, brilliant. So now let's go quickly to the next. What best describes your highest education in mathematics? I'd like to understand the audience I have here today. What best describes your highest education? Okay, we have 1 PhD, brilliant. Okay, a master's. Okay, 1 undergrad. Okay, we see the the real time changes. Okay, we have a good number of undergraduate students. Can we get a few more responses before we go to the last? Okay, so it seems we have quite good. So it's a wide range, right? At least someone from high school, then we also have PhD, but a good number have undergraduate background. Brilliant. Now let's go to our final question. What are your expectations from today's talk? What are your expectations from today's talk? What are your expectations? So just a line or 2 about your expectations from today's talk. What are your expectations from today's talk? What are your expectations? Okay, great discussion. So as I mentioned, it's not going to be a lecture. I'll try to make it interactive. So I will be asking you for your inputs and I'll also be listening. Okay. Okay, you want to understand the usefulness of mathematics in machine learning. Okay, leverage math knowledge in data science. Okay. Yeah, so it's still around the topic, right? You really want to understand how mathematics can enhance your knowledge and skills and data science and machine learning. That's the name of the group subject. So thank you. Also, I'll stop sharing the screen so I can go to my slide. So hopefully by the end of the talk, you get what you're expecting from this. So let me share my screen. So okay. Just give me a second. I'm sharing my other screen. Seems to be taking a bit longer than I expect. Okay, so it's still loading. So I like to write. I'm a mathematician, not a data scientist or an AI expert. So as a mathematician, I like to either use a board. In this case, it's remote. So I like to write. So I'm trying to get to my other screen to work, and it's still loading. Maybe I stop and start again. Oh, sorry. I guess I will need to be made. It says only the host can, I don't know, but I was able to share. So can you make me a host on my other device, the one that I'm speaking from, the one with the volume? It seems I need to be made a host. Sorry, a co-host. Okay,
Yes,
brilliant.
I just will be a co-host.
Yeah, thanks so much. Yeah.
Yay, we can see it now.
Oh, you can see my screen, brilliant. It shows it's loading on my so yes. A bit of warning. I'm speaking to you from home. I have a baby who might scream at any point in the meeting, and so in case my baby screams, I'll have to attend to him. So thanks very much for the invitation. So my talk today is on machine learning, the foundations of. Okay, so as mentioned, I'm a mathematician, and my talk today is going to talk about the foundations of mathematics in diverse fields. In this case, my audience is machine learning and data science experts. So here's what I want to start with. So about my background. So I'll talk a bit about my background. In terms of the outline, I'll talk about my background. Then I'll do some maths. Then what next in terms of the future, right? What next? And that will be the end of my talk. So let's talk a bit about my background. So in terms of my background, since we have an audience starting from high school to PhD, I'll start from my high school. So let's have a timeline here from high school to PhD. Okay, so from high school to PhD. So in high school, who can guess what my major in high school was? The subject I majored in high school. Any guesses? So let's use a chat box for this. Any guesses what I studied in high school? Any guesses in the chat? Okay, I see business, I see science. Okay, arts. Okay, brilliant. So at least one of them is correct. So actually, I studied business. So I'm saying this to highlight that irrespective of what subject you studied in high school, you can become that scientist or that's whatever career you aspire to be. So I'm actually a business student and scientist. So I went to business school and I studied business. I wanted to go into accounting, wanted to go to the business school, but in a blessing in disguise, I didn't make it to the business school. So what did I study? So I went to the University of Ghana, where I studied mathematics, of course. I studied economics and two other subjects, sociology and theater arts. So at the university, of course, maths was very challenging, but I found it very fulfilling when you are given a maths work and you go through and you're able to get the solution. It makes it very fulfilling. But I didn't know I could pursue it maths to a very high level. So in final year, when head of department asked me to major in mathematics, I told her, what do I do with maths? So I want to keep things safe. So I finished with a Bachelor of Arts degree in mathematics and economics. Fast forward, I still didn't know what I wanted to do, right? AIMS had just opened in Ghana. So one of my mentors asked me to apply to AIMS. So if you don't know AIMS is the African Institute for Mathematical Sciences. We have centers all across Africa. And I went to AIMS. And for me, the reason I went to AIMS was to see more maths and see if maths was really something I could pursue to a very high level. And AIMS is a very intense environment, right? You meet students from all across Africa, and lecturers come from top universities abroad. And there was this lecturer who came who was teaching algebra. I really love algebra. I used to ask questions as early as 6 a.m. I would be there knocking on his door, asking him questions about algebra. So I still finished AIMS and I wasn't sure what we wanted to do. So there was this opportunity that was opening at ICTP, which is the International Center for Theoretical Physics. So Uli, my mentor, asked me to, okay, maybe you could explore going there for a year and see more maths, right? You've learned maths at University of Ghana, the Ghana level, you go to AIMS, African level, now you have to go to the global level. It was very challenging. I'm sure those of us here who have transitioned into educational systems abroad will talk about the challenges, right? So I went to ICTP, and ICTP maths was really hard, and I asked myself whether I was really good at it, if this was something I could really continue with it. But that also presented an opportunity. So at ICTP, I realized that, okay, I really wanted to pursue maths to a very high level, but there was this barrier, right, in terms of where I had to study and in terms of the funding for it. So there's usually very little funding to go to study, especially in the UK. So I applied for the Schlumberger Foundation Faculty for the Future Fellowship. So I'll just put it here, since we have a good audience of women here. This is something you can check out. Schlumberger Foundation Faculty for the Future Fellowship. So this supports outstanding women in STEM to study at top universities abroad, with the goal that we return to our home countries to promote the teaching and learning of STEM courses, because we didn't see a lot of women in STEM fields. Imagine going through your whole education and not having a female math lecturer, since I'm math. My first female math teacher or lecturer was at the university in third year. I'm sure it's similar for most of us. So I was awarded the Schlumberger Foundation Faculty for the Future Fellowship. So if you are here, just Google it and you are looking for PhD funding. The applications usually open in September. So I was awarded one to study at the University of Glasgow. So in Glasgow, that was where I studied for my PhD, and I graduated with a PhD in mathematics. Then fast forward, after PhD graduation, I returned home to Ghana. So from PhD, okay. So from PhD, I returned home to Ghana. And in Ghana, I got a job in Ghana, AIMS Ghana. So I actually returned to AIMS Ghana, where I was an AIMS Google AI postdoc. Now, so just a bit of jokes. When I updated my LinkedIn profile that I was an AIMS Google AI postdoctoral fellow, some of my colleagues understood that I was working with Google. So everyone got excited and they were sending me congratulatory messages that, oh, Angie, how did you get into Google? Yeah, but no, my postdoc was actually funded by the Google AI office, which had just opened in Accra. So that leads me to my connection with machine learning and data science. So as part of my postdoc, I was supposed to teach mathematics for machine learning, and I made my first stop in Rwanda in the Army program. I see a lot of alumni here. I see Deborah, Khadija, the rest. So I had to teach mathematics for machine learning. Personally, I am a pure mathematician. My research is really abstract, so it was a very big challenge for me, right? But in life, we take up challenges, right? So I took up that challenge. Usually at AIMS, I teach a course in linear algebra. But now I had to teach linear algebra to AI students, and I remember the first day I walked into class in Kigali, students were wondering, okay, who is this, right? Because in the Army program, you're expecting people from Google or Facebook to come and teach you, but this is what, this young lady who just some mathematician coming to teach me. So that leads me to this. So that was where I drew the connection between the abstract mathematics that I taught and the AI that has become very relevant now. So that leads me to the next part of my talk. So in the next part of my talk, I'll talk a bit about the math that I teach, which is mainly linear algebra, and how they became useful to the AI. So in this case, the machine learning and data science audience here. Okay, so this part will also be very interactive. Okay, so let's start with data. So let's use a chat box now. What kind of data do you work with? What kind of data do you work with? Can you put your answers or your in the chat? Do you work with? What kind of data do you work with? Images, okay. Images, okay. I see images, biological data, audio, brilliant, signals, tabular data. Yes, I want a wide range. Let's audio, chemicals. Wow, okay, numerical data, languages, brilliant. So data. Now, when you think of data, we all, before you can work on it, you have to find ways of what collecting your data, right? So collection, right? You have to collect your data once you have it, right? So the first thing I teach usually in my linear algebra course is something we call what? Vectors. I'm not going to bore you with what a vector is in maths, right? So what is a vector? So geometrically, so one thing I learned from teaching the mathematics for machine learning course was that when you learn with pictures, it helps in building intuition and understanding. So I'll try as much as possible to look at that in terms of the geometry of things, because when you see things, it becomes easy. I'm not going to ask define things rigorously as we do in a math class, right? So what is a vector geometrically, right? Geometrically, or maybe let me wait for a few comments from you. What is a vector geometrically? Any comments? What a vector is geometrically? Just type in the chat box. What do you think a vector is geometrically? So if you were in the mathematics for machine learning course and I asked for this, okay, I see a line, okay. Yes, what do you think is a vector? A vector, not the math rigorous definition. Representation represents a direction, okay. What else? A set of points, okay. What else? Array, okay. Okay, brilliant. So let's go. What is a vector? So for my understanding, the vectors are just what? Objects which you can scale or add. Of course, you can also think of them as what? Arrows in space, right? So you can think of them as what? Arrows that you can what? Move around, right? But I think of vectors as things that you can what? Add or scale. Okay, so that's geometric, right? Things that you can add or scale. So when we talk about the data that you were talking about, right? So data can be collected in what? Objects which we can call what? Vectors, or yes, vectors more broadly. And with that, that means what? We can add them or what? Or scale them. Of course, there's the more rigorous definition, right? But geometrically, just think of vectors as objects that you can what? Add or scale. Now, this is very important, right? The ability to add them and the ability to scale them. Those are the key things that helps you to do whatever you are doing with it in data science and machine learning. So this broad definition means that your vectors, right? Very often in data science, you collect your data in objects which you call what? Vectors, or you could also think of them as what? As matrices, right? Now, when you collect them in these objects, what do you do with them? You want to what? Analyze it to get what? Things from it. So first we collect data, then afterwards what? We analyze them. Now, when you are going to analyze data, What does it mean to analyze data? Now, let's say we are collecting data here. So now, when we started the talk, and I talked about finding out the backgrounds of my audience, right? So let me say I have a vector called audience background, right? Audience background, right? Now, in my first entry here, I'm going to record how many students had what high school background, how many here have what undergraduate background. Nextly, those who have what postgrad, and finally those who have what PhD. So practically, from what we interacted with at the beginning of the talk, right? I saw only one person with a high school background, about 7 with undergrad, then let's say about 4 with this, and 1 with a PhD, right? Now, when you collect this data, so that was from this talk. But yesterday I was at another conference where I was with teachers, right? Now, for the teachers, for instance, I was collecting another form of data from them. So, for instance, I was collecting data on how many of them were teaching in high school, how many of them were teaching in primary school, and how many of them were teaching in senior high school. So maybe let me just let me just go to my next page. So let me first, so for my first vector, I had 1741. So that was for the audience, right? Now, if I consider the data I had yesterday, which was talking about how many teachers. So here, my first entry, I'm looking at primary school teachers. In the second entry, I'm looking at junior high school teachers, and here I'm looking at senior high school teachers. So we had 150 teachers. So let me just make it even and give them 50, 50, 50. Now, if you look here and you are trying to analyze data of audience, so if I want to analyze data of audience in talks, audience in seminars I give. Can I work with these two data using the idea that vectors are things that I can add or scale? Can I add A to B? Can I add A to B? So Frank says yes. So use the chat box to let me know what your comments are. Amina also says yes. Can I hear from the rest? Okay. Deborah says no. Okay. Rihanna also says yes. Okay. Alex says no. A few more. So it's quite a blend, right? Okay. Quite a strong no, but there are some yeses in there, right? So our time is really fast spent, so I won't ask you to tell me why it is or why not, right? So let's look at this very clearly, right? Now, if you look at this first vector here, right, you realize that it has 4 placeholders, right? So there's something that has to do with 4 here. It's related somehow to 4 here. But if you look at this other vector here, it has 3 placeholders, right? So it has something to do with 3, right? Now, how are we going to add these two? It will become impossible, right? Because if you are going to add 1741 to 50, 50, 50, right? Usually the convention is that you add things in the same row. Then what happens to this last entry here? There's nothing there, right? You can't just put 0 in there, right? So which leads me to this. So vectors, if you have a good understanding of mathematics, right, it tells you that this vector here, A, lives in a certain space where there are 4 entries that needs to go there, and this leads into a space where there are 3 entries that needs to go there. It has something to do with the dimension of the space. So it has something to let me just write down vector space. So these vectors live in a place where we call vector space, and vector space have something we call the dimension. So think of the dimension as how many entries you put in the vector. Okay, so in this case, this vector we had, which was what 1741, lives in something with what? How many entries do we have here? We have what 1, 2, 3, 4, something with what 4 entries. So loosely we say it's something. It belongs to 4-dimensional what space, vector space, but the 50, 50, 50 belongs to something which belongs to what? A 3-dimensional space. Okay. So that's the first thing we need to take from this talk, that you can add vectors in what different dimensions. Okay, so mathematics is very well defined. Okay, so when we even talk about addition, I was telling you that addition means that you add entries in row 1, entries in row 2, entries in row 3. Now where's the row 4? Okay, so the dimension of a vector space. So a vector space is what where vectors live. Okay, where vectors live. Okay, so the dimension, think of them as in this case the number of entries here, but of course more rigorously, the dimension of a vector space is related to something which we call the basis. I'm sure you've heard basis somewhere, which we might come to get into the end, right? More rigorously, right? A basis is what? So you have vectors living in some space. So basis is, think of them as the atoms that you can write any vector as a linear combination of them. Now, a basis requires that those vectors are what? Linearly independent, and also they should what? Generate the whole space, or generate the whole space. The whole space. So I really wanted to mention basis because it has something to do with the work you do, right? Who has heard of the word orthogonal basis before? Orthogonal basis. Who has heard this before? Orthogonal. Just type yes in the chat box. Orthogonal basis. Who has heard orthogonal basis before? Just type it in the chat box. Have you heard the word orthogonal basis before? Just type it in the chat box. Okay, Rachel says yes. What about the rest? Orthogonal basis. Amina also says yes. Anyone else? Khadija says yes. Anyone else who has heard about orthogonal basis before? So orthogonal basis is relevant for you as machine learning and data science persons, right? Why? Because when you are working on your data, sometimes it helps to move from one basis to the other. We can move from one basis to the other. There's more rigorous math to do with it, and also more rigorously, every vector space has a basis. That's how come we can always find it. But of course, sometimes it's difficult to find a base. But orthogonal basis makes it easy for you to do certain operations. I didn't define what a matrix is, right? But there are very strong theorems in mathematics that tells you that when you have this property, then it tells you when a matrix. So for instance, if you have a matrix and you want to, which represents some transformation you are doing in data science or machine learning, and you want to perform that transformation n number of times, right? It helps if that matrix is in a certain form where you only have entries on a diagonal, and when you have the when you have this, and it becomes easy to do that transformation. So it's very relevant when you're doing what's orthogonal projection and all that. So I'm not going to go too much into it. So because as pure maths, we do all these rigorous things, you don't need to prove them, right? You just pick them and use them, right? But it's important that you understand that's what the basis means. That's what every vector in that space you are working with can be written uniquely as a linear combination of these basis vectors. Okay. Fast forward, let's go a bit quickly. So I mentioned what dimension. So as data scientists, you like to visualize things, right? So we hear a lot around us. Oh, there's 2D, 3D. So people ask, what is D, right? D is just the dimension, right? Which is more rigorously the number of elements in the basis. So here I mentioned that more loosely that, because we have 4 placeholders here, this belongs to a 4-dimensional space. Because we have 3 space holders here, we have 3. But of course, more rigorously, The dimension is just the number of elements in the basis. Okay, so there's very deep theory going behind it, but of course, you are just applying it, so you don't need to understand all these. But when we are visualizing data, right, in 2 dimension, it means that what you are visualizing it with what? You only need what? Two components to describe it, right? So 2 components to describe it, you just need what? Your X and your Y plane, which we looked at in primary school and junior high school, right? But when we go to higher dimensions, we look at what, for instance, 3D, it means that what you need what 3 coordinates to work with. And then you need what X, Y. I don't know why we use X, Y, and Z, right? As mathematicians, every time we have X on our page, someone keeps asking, yeah, why X? Yeah, we never find our X, right? Yeah. So in 3 dimension, you are describing your vector and with 3 different coordinates, right? But what about higher dimensions, right? So if you want to yeah, maybe someone should tell me, can we visualize 4D? So now I mentioned 3D, 4D. Can we visualize 4D? 4D. Can I draw things in 4D? Let me hear from you from the chat box. Can we, so maybe let me write down the question. Can we visualize data in 4D? Data in 4D. Let's hear from you in the chat box. Can we visualize data in 4D? Can we visualize data in 4D? Okay, Rachel says yes, it can, yes, cannot easily be interpreted. Okay, Mebasion also says yes, Adra says yes. Let me hear from the rest. Can we visualize data in dimensions higher than this? Can we visualize data in dimensions higher than this? Or a few more, can we get a few more contributions? We have only 3. Can we visualize data in 4D? Okay, Khadija says, I'm probably just wondering what about like how it says, yeah. So yeah, I've not even thought about this, right? So Z is usually the last alphabet in the English world alphabet system, right? And if you think more deeply, there's no alphabet after Z, right? Which kind of gives some intuition onto, you see, for 2D we started with X and Y, and 3D we extended it to the right, X, Y, Z. So can we go a bit further from Z? Yeah, maybe that should give you a clue that okay, from my understanding, maybe I might be wrong. You do more of the practical work, but from my understanding, I don't think so that you can visualize data beyond these, right? But the real life data that you work with, maybe let me find out from you, how many components or in what dimension or do these data live in? What kind of what number of entries? So my next question, what is the dimension of the data you work with? Of the data you work with, you work with. Just type the number in the chat box. So from the beginning, some said you are working with images, some are working with chemicals, some are working with audio, some are working with signals. Yeah, what is the dimension of the data that you work with? Okay, Deborah says 2D. Okay, Amma also 2D. Most images, most of the time 2D with images 3D. Okay, can we hear from the rest? What is the dimension of the data? So you saw the data I collected at the beginning of this talk. This data, which was talking about the audience, right? This is a data in 4D. This one was a data in 3D. What kind of data do you work with? Oh, I see a lot of tools. Can I have a few more? Does anyone work with data higher than 3? Can you put in the chat box? Can anyone work with data higher than 3? Anyone work with data higher than 3? Okay, it seems not, right? But for real life data, we have components more than 3, right? So you could have as much as you want, right? But of course, for you to understand data, it's important to visualize it, right? So that led me to the second part of the talk, that which is about multivariate calculus. So when I was teaching the mathematics to machine learning course, it was in 3 aspects. The first one was in linear algebra, which was about the vectors and the dimension and things we just talked about. But the second part was multivariate calculus. So calculus, when we were growing up in high school, we were doing what? Dy, dx. They will tell us that what's the derivative, right? Or the derivative, will give you some long definitions of what it was, f of x minus f of x plus h minus f of x over h limits, all these abstract things we're doing, right? But actually, right, you can think of them. So let's start in 2D. If you have so in 2D, right, if you have the equation of a line mx plus c, right? Dy dx. So what we did with differentiation using whatever rule you were thinking about, chain rule and all, power rule and all that, was just what. So if you have this and you want to find dy dx is just what? The slope of this line, right? Which is just what? The change in y over what? The change in x. Okay. Which was just the slope of it. But of course, when you go to more higher levels, we use differentiation. Of course, here I have my function as a function of what? Of x. But as you can see here, there's multi here, right? That means your function can be a function of a lot more variables. So you could have what? A function of what? Let's say x, y, and z, or even in real life you have what? Functions of more data, right? So what the calculus we're doing with the differentiation, how relevant is it here? Its relevance has to do with what we call optimization. So now when we had our data, so we mentioned that for our data, there are different things we can do with data, right? You could want to fit it to a model, right? So you can what? Fit your data to a model, right? So you want to fit your data to a model. So I'll just use a 2D representation. So let's say you have your data points scattered all around here, and you want a model. So here you want a line which best describes your data. So in fitting your model, what do you want to do? You want to ensure that data fit data to a model with what? Minimum error, right? You don't want a model which is very far from what the real life data, right? So what do? It means that you want to what? Minimize what? Your error. But in this case, if the model I'm fitting is a line, right? Which means that what? I want to what? Minimize how far my data points are from what? This line. So if here I measured my distance in this, I want to find what? The line, the model which has what? The least error when I look at this. Now, how do you do this? You do this by what? Projecting what? Your data points what? Onto this line. And all with doing this, it involves what? Some calculus, right? So what you are doing is like you're minimizing the error, which has to do with what? The distances between from your data points. So you are going to use some calculus here. But of course, you when you go to more higher levels, when you want to visualize data, your data is, no one mentioned a data higher than 3D, right? Now, if you had data higher than, let's say, in 1,000 dimensions, right? Of course, you cannot visualize that now. Maybe with more research, you'll be able to break these, but for now, we can't visualize beyond this. But visualizing data also helps you to draw inferences, right? To understand it very well. So that led me to the final part of the course that I taught, which was what? Principal component analysis. So I mentioned that in real life, data is usually in higher dimension. Now, applying our knowledge in linear algebra and multivariate calculus. So if you have what? Higher dimensional data, right? You'd want a way to what? To reduce dimension from what? A higher dimensional data to a low dimension that you might to visualize. Okay, so low dimension means that's what you want to reduce it to either 2-dimension or 3-dimension. I mean, and so as the name suggests, right? So you'd want to what? So let's say you want to move from what? 1,000 what D to what? 3D, right? So as the name suggests, what? The principal component. So your data is described by what all these what different dimensions, right? So if you recall, I said for my first data that I collected, right, which was a 1741, right? My first dimension, my first more loosely here entry here was recording what? How many what? High school students were here. Then here my next one was what? Undergrad. Then here we went to what? Postgrad, and what? Finally to what? To PhD, right? So each of these dimensions describe what? Some aspects of my these entries here. Now, if you have higher dimensional data and you want to visualize it, you want a way of what? Reducing these 1,000 dimensions to what? Let's say three dimensions by what? Picking up what? The dimension, the key, as the name suggests, the key dimension which best describes your data, but by doing this with what? Minimum error. And that applies what? Both your multivariate calculus. You remember the bases and the orthogonal bases and the projections I was talking about. It involves all these rigorous calculations, and that helps you to find your orthogonal my time is almost up. But finally, I wanted to talk about one more application where when I was preparing for this, I've been hearing about what support vector machines, and whilst preparing for this, I said, okay, maybe I can also learn something new, right? So whilst preparing, I realized, okay, there's vectors there, right, which we saw initially as an object where we collect data in, right? But what does this all mean? So I was reading, and it was similar to what I was saying. So when you have data, you want to find a way of classifying your data. So for instance, you have your data points scattered. So you want to find some way of classifying your points so that all points which are above your line belong to one class, those below your line belongs to another class. You can go to a higher dimension, let's say in three dimension, you have your data points scattered, but then you also want to find a way of separating your classes of data. Now, what are these lines that I've drawn here? So maybe let me just use it. So these here, I found out to be what we call hyperplanes, right? So wow. So when I saw hyperplane, it took me back to a course I did in algebraic geometry. So in maths, algebraic geometry is just the study of solutions to equations, right? So a hyperplane. So we saw what a vector is. We said it lives in a vector space. So a vector space has a dimension, which we said was the number of elements in the basis, right? So if you have a vector space of dimension, so if you have a vector space V, vector space of dimension, I'll finish in a minute so we can have time to discuss some questions. So of dimension N, right? A hyperplane, right, is what we call a subspace of V of dimension N plus 1. And sorry, N minus 1. So I was like, oh, okay. So because I've been teaching, so if the keyword here is subspace, right? We have a vector space, then we have dimension N and dimension N minus 1. So in my linear algebra class, when we start with vector space, we talk about subspaces. A subspace is what? A subset of a vector space, which is also a vector space. So think of your vector space, which is what your x and y axis, your plane, right? Subspaces of this will be all lines which pass, not just any line, right? All lines which pass through the origin. So here's your origin, the point 0, 0. Now, if you go to 3-dimension, yeah, subspaces of these will be what? Planes and what? Lines. So the plane, so here's a 3D, a plane will have what? Dimension 2, and a line will have what? Dimension 1. And I actually found out that when you are solving for the hyperplane, you just use what? Solving for what? Coefficients which satisfy what? Certain equations, such as what? This, and those coefficients will help you to find your hyperplane. So why is this important, right? So you want to what? Maximize what? So we said we wanted to classify your data points into what? And you want to do this by what? Maximizing what? The space or the margin between two, so that it's not as if one is in both places, right? But one is fitting in one place, one class, and the other is in another class, and that actually involves some math. It took me back to algebraic geometry, but also in real life, data is not always linear, right? But so if it's not linear, then you have to what? And I found out there's something called like the kernel trick, where you find a map which maps your data into a linear what? A linear higher dimensional what? Linear space, where you can actually find the hyperplane to do this. And yeah, and an example of that kernel trick is just a radial basis function. So I was like, oh, okay, so the functions that we usually talk about as a function being a rule which assigns what an element in the domain to another element in the codomain is actually relevant in real life. So I think I'll just pause here. Otherwise, I'll talk for the whole time and listen to you if you have any questions. So I hope I gave you a bit of gist into some of the math that is relevant. And I'm sure there's even more, right? Because now personally, my research is in something which we call Hopf algebras, which is really abstract. But just recently in our research group meetings, we found that these structures can actually be found in what? Language syntax, which is very interesting, right? The way we bring together words to form sentences and things in languages actually has this abstract structure of algebra. So it's something we are now going to explore to see how it's going to become important in natural language processing and all these new things that are coming up. So I guess I'll stop here. I can go on and on, but it's important to stop here and hear from you what your comments are and what your questions are. So let me just stop sharing my screen so we can also hear from you. So thanks so much for your audience, and I'm happy to respond to your questions, comments, suggestions.
Thank you very much, Dr. Angela. This was a really interesting session. Like the examples just took me back to those days when you were teaching us linear algebra. Like At that time,
Yeah.
I was starting again in mathematics, and sometimes I'll just be like, what am I actually supposed to use this for? But like moving forward, I could see that there were so many instances where I had to apply this in whatever I was learning. Even at this point, like I'm still applying all that knowledge. So it was a really great discussion. I'm sure that many other people here learned from that as well. So at this point, if you have any question, just feel free to unmute and then ask directly to Dr. Angela, or you can just put it in the chat and she'll respond to it.
Yeah, so I have a question. Thank you so much, Doug, for this session. It was really insightful. So my question is not really related to the content, but like a general question concerning academia. So I'm a software engineering student, but like our course outline is not focused on mathematics. We don't do more of mathematics, so like just the basics of mathematics. But like going into ML, you get to see that you really need to understand the basic concepts of calculus, statistics to be able to thrive. So I'm wondering, in this case, after graduation or probably trying to further into your master's, PhD and all that, how do I thrive in that field in order that I don't miss out or I don't miss out on certain opportunities that because I didn't have the background in mathematics, although I did some mathematics back at high school. So I'd really be glad.
Yeah, thank you so much, Bernice. So one good thing has come now in this era is self-learning, right? So personally, I learned about mathematics from machine learning from Coursera, right, which is an online platform. So I would say that make good use of the resources available. So yeah, there are talks on YouTube, and I mentioned Coursera. These are places that you can learn, right? They have practice sessions that will help you to do so. So yes, you might not have furthered your education in maths from high school, right? But that shouldn't stop you from understanding the maths that you need to be a very strong software engineer. So I would say invest a lot of your time in self-learning using these online platforms. Of course, if you also need some other more rigorous understanding, there are people around. If there's a way I can I can help you understand, I'm sure I can, or even people around you. So make good use of the resources available online to do some self-learning, and don't just give up that because you didn't do maths. That's just try as much as possible to learn as much more as you can.
Follow-up question. So do you think it's going to be a disadvantage concerning like if you want to further into something that is related to mathematics or with the online courses and everything, will that be able to push up any application you might want to do in the master's level and yeah, just advancing in general?
Sometimes it depends on the requirements from the universities, right? Some universities you can go in without having a mass undergraduate degree, or they do allow you. Others to they only once your knowledge, right? They will interview you, so they will be sure you really understand the maths behind it. So it's diverse. It depends on the university. Some will require that you are taking some specific maths courses. Others will just require your technical knowledge of it. So just make sure you understand the maths behind it, and I'm sure you find a place where that is enough to get in. You don't really need the degree in maths to get in. Yeah. Hope it answers you.
Yeah, thank you so much.
You're welcome. Yeah, there are some questions in the chat box. Yeah, so I'm not an AI person, so I'll leave the AI people to actually explain the difference between PCA and SVM. Personally, I only knew PCA until today when I was preparing, and I realized, oh, there's SVM, which so I'm yet to think deeply into it to see what differences are. But if someone else knows, the person can just respond. The course on Coursera was mathematics for machine learning, if I'm not mistaken. Yeah, mathematics for machine learning. Okay. Yeah, I think someone just responded, yes, it's mathematics for machine learning. Yeah. Any other question?
Yeah, about
Okay.
the PCA and SVM question, my brain is kind of dead at the moment.
Yeah,
But
yeah, yeah.
yeah,
You don't have to. There are resources that we can Google or see, but if you
yeah.
want to answer,
Yeah, the thing that just comes to my mind right now is that they are both for like dimensionality reduction. So if you are working with data in a higher dimension and you want to be able to reduce it such that you can work with like more like less computation, then PCA and SVM can come in at that point. So that's just sort of what I remember for now.
I'm sure maybe one will work better in certain settings, right? Or maybe for certain types of data, but I can't really say much
Yeah.
about. Yeah, any other question, comments? Yeah, I was a bit scared coming in here. I was wondering how you have all these data science people, and I'm coming from my maths background, and how am I going to fit? But the hour came so quickly, right?
Yeah.
Um,
Does anyone else have any questions? Or do you want to share like any experience with like combining math and machine learning? And I think for me, there was this instance which was really interesting. And like this is the first chance I've had, like just when you were talking, it just came into my mind. So there was something I was like applying for, and then they gave me like a paper to summarize. And this paper was like mostly about benchmarking and machine learning. Because like when you train a model, you have to benchmark it against like a big data set and stuff like that. So the question was sort of like, what is the problem with benchmarking? And the thing that just came to my mind was that in maths, you know, we have the law of large numbers. As the sample size like gets closer to the population, then we are getting closer to one. So I was like, applying this mathematics to benchmarking, we can easily just see that if you have a data set that is very, very small as compared to the benchmark, you wouldn't expect to have like a model that is trained on this little data set to work perfectly on the benchmark, because the benchmark has like a lot more samples than you have. So in order for you to get better, you need to sort of like train with more data, at least as you approach the size used for the benchmark, then you can start to get accurate results. And I think that was like really interesting, even for me answering the question. Like, I just like the fact that I was able to connect Star Maths to it. So yeah, I think at the end of this session, I can agree that maths is really important for machine learning. So getting to understand these basics like Dr. Angela has taken us through is really, really important.
maybe one final thing to say. So very often when so I was studying, I've met I mean meeting people who have had PhDs and let's say maths or other related fields who have moved on to industry, right? What helps them a lot is that they understand what they are doing. Once you understand what you are telling a computer to do, you give the right instructions. But if you don't understand how the computer is thinking, then you might be telling it to do something wrong, or you might not even be understanding the output it is bringing to you. So as much as we are enthusiastic about machine learning, data science, let us take some time to also understand the math behind it and to understand how the machines are thinking. Once you do that, it gives you um, a step, you go a step ahead of everyone else, because you really have deep insights into what is actually happening, what you need to do to get your machine to do the other. So yes, the way math has been taught for a long time has been very boring and very theoretical, but and now we have these interesting examples to inspire more of the young people to do this. So hopefully this helps you to yeah in your work. Yeah, that's you also need to understand the math behind it to understand how the machines are thinking. Yeah. Okay. Yeah, I see group photo, right? Yeah, I was going to
Yeah.
ask whether
I think we are at that point. Obviously, we all enjoyed the session and we want to keep the memories of the session. So we think it's important to turn on our cameras, like strike our best pose and then get that group photo. I see a few people turning on their cameras. Let's keep it up. Yeah, just change.
I see very few cameras on.
Yeah, I'm sure people are still turning on their cameras, putting on
Yeah.
makeups and all that.
Yeah, it's a weekend, right?
Yeah.
Oh, okay. I see a first camera on and Vera, yeah. Few others. Good to see you, Rakib, Rama. Yeah, Rama sent me the invitation, right? Yeah.
Yeah.
Thanks, everyone. Have you taken the screenshots?
No, not yet. I'm just waiting for a few more people. Guys, let's turn on our cameras and get the group photo, and we are done. I see Amina. At this point, I'm just going to mention names from the chat so that people turn on their cameras. Lucy, Rihanna, Sarah, Wendy. Yeah, I think
Rachel
we
as well. Rachel, we haven't seen yet.
yes, Rachel. Rachel is here as well. Joanna, Jude, Frank, Eunice, Eric. Okay.
Even Deborah's camera is not on, right?
I think she's multitasking at this moment. I think she's probably in another meeting.
Okay, that's fine. But thanks so much for the invitation. It's do you always meet only on Saturdays or you meet on other days?
So
Only
it's
on
usually
Saturday.
on Sundays, once every month. Yes, but we do have other programs. Sometimes you have like panel discussions, which can go on like twice in a month or so.
Yeah, wow. Kudos, you're doing phenomenal, amazing, right? So,
I think we have enough people now, so I'm just going to take the screenshots from my end. So just do your best pose, and yeah, I'll just grab it from here. So
Cheers,
1,
everyone.
2, 3. Yeah, I think I've taken about 20 photos already. So yeah, that brings us to the end of the session. Thank you everyone for joining, and to be able to like get information on our next meetups, just follow our social media pages. So we are on LinkedIn as Men in Machine Learning Data Science. We are also on Twitter as WeMoDS Accra. You can also join our meetup page to get notifications of events that we have in the future. And we are also having our first Mass for Machine Learning Bootcamp in partnership with AIMS. And this is completely run by the students of AIMS Ghana, which we are really looking forward to. So if you want to participate in the coming ones, or you've already applied for this one, just check your inbox and you'd get a message confirming if you are part, and if not, you can always apply for the subsequent one. So yeah, have a great weekend, everyone, and we hope to see you for our next monthly meetup. Bye. Thank you very much, Dr. Angela, once again.
thank you. Bye.